Hi, this is J Inkawhich from Duke University. Our paper is number 962, The Untapped Potential of Off-the-Shelf Convolutional Neural Networks. Novel methods like neural architecture search yield powerful models, but they are static at inference time. We believe that it is unreasonable to expect one static configuration to be optimal for all inputs. This is due to factors such as image scale variation, context, and orientation. Our hypothesis is that if we allow models to have a dynamic receptive field during inference, the model will have a significantly higher upper bound of generalization. We also believe that off-the-shelf models can extract meaningful features from more inputs than they are given credit for. Our goal is to investigate the upper bound of performance if we allow models to be dynamic at inference time. We consider three dynamic attributes: kernel stride, dilation, and size, and we consider four different dynamic layer locations indicated by A, B, C, and D in this dynamic ResNet 50 figure. To compute the upper bounds, we use a comprehensive evaluation procedure where we run each test sample through all possible model configurations and rank the outputs based on quality, which is essentially equal to the probability of the target class. We can then track the best, median, and worst case accuracy on the ImageNet validation set. Here are our main results. Table 1 shows the worst, median, and best case accuracy for common models. Note how high the best case accuracy is compared to the static default accuracy. Because a perfectly optimal selection policy is not feasible, it would be nice to reduce volatility between the worst case and best case accuracy. We can do this by using a short random option fine-tuning stage to make the models more robust to suboptimal configurations. Table 2 shows that this is an effective way to reduce volatility. Due to significant redundancy of predictions resulting from different configurations, a natural question is, do we really need to consider all possible permutations? Using a greedy algorithm, we created the number of permutation versus accuracy curves in figure 3. And observe that even if we only consider a handful of configurations, we can still significantly improve our upper bound of accuracy. Finally, figure 4 shows that by reducing kernel size and increasing kernel stride, we can effectively improve the average efficiency per sample during inference. The gray dots indicate all possible static configurations of a ResNet 50 model, whereas the green and blue circles indicate the performance of the accuracy-focused dynamic models from before. If we specifically choose the most efficient dynamic configurations to achieve our same upper bound accuracy, we get the star markers and find that these models are capable of the same accuracy level with significantly reduced max per sample. We can use this comprehensive evaluation procedure to explore model configuration preferences. A common belief is that the larger the input features, the larger the preferred receptive field should be. To test this, we resized the standard ImageNet validation images ranging from a 4x downsample to 4x upsample and observed the most preferred configurations from our dynamic models. The stride dynamic model shows the expected trend. As feature scale increases, larger strides are preferred across layers. However, the dilation and size dynamic models actually prefer a smaller receptive field in the shallow layers with larger receptive fields in the later layers. This analysis shows that the optimal receptive field is not as straightforward as it has been made out to be, and receptive field growth is much more meaningful than the scalar final receptive field. From this work, we take away three important conclusions. Number 1, even off-the-shelf models can significantly outperform their static variants with appropriate configuration selection. Number 2, performance of existing dynamic methods do not nearly approach the upper bounds that we found. And number 3, optimal receptive field for an input is not straightforward with respect to feature scale. Well, this work simply exposes the strong potential of inference-time-dynamic models. In the future, we hope to accurately automate the configuration selection process to exploit the performance bounds that we found on unlabeled data. Thanks for listening.